tell him we're in HJP. So here he is, GSS leader. He will continue to use this small little board here on the left to remind you of when GSS sessions are. So come up, you can grab his contact information, when they are, and that sort of thing. So welcome, thank you very much for finding us. No thanks to me, all of his own accord. He already found that he walked in, and I just didn't know who you were. Okay. So we went to discussion yesterday, and I'm getting lots of questions in my office about acid-base chemistry. That's really good, so keep them coming. The pKa problems that are online, which now are rightfully placed, I don't know what the system did, but I moved them. I hope they didn't move themselves back, but I moved them to the weekly quiz folder. Those are problems my 231 students should be able to do as well. So darn well you guys should be able to do them. So if you're having any trouble, you got to come in. You got to make sure square away the acid-base stuff. So Kim will be meeting the rest of you in discussion tomorrow. Please don't forget that use testudo to find the rooms. The room movement is probably not easy either, right? You gotta pick yourself up and move on out, right? And the announcement was put up about discussions as well. It's a reminder, reminding you there's no discussion on February 13th, which is the day after our reassessment. That's all I have to say. Are there any other announcements that need to be made before or questions you have? I feel like it's church, right? I was just thinking, God, I sound like a priest, you know? That's all the announcements I need to make. Are there any more announcements? I'm literally going through this in my head, and then I'm like, these people don't have announcements, but you may have questions. So are there any questions that anybody has before we move forward? No questions. You guys are a class of not a lot of questions. I hope we can change that, because it's really good to ask questions. It's just a good thing. All right, so today we're going to be talking about spectroscopy. That's what I promised you. We would come in and we would review pretty quickly in one day the sort of basic theory, not totally crazy anything, right, about spectroscopy. So we're going to review that really quick on Friday. Just a heads up, we're going to be in here with NMR packets that have mass spec, IR, and NMR spectra on them, and you're going to be asked to come up with the structures de novo. With all that information, you're going to be asked to generate structures. I'll be going over how to do that and how you can do that. If you're a spec guru, then come get the packet, sit quietly, and do all 9 problems in class. I'm all good on that. But just try not to be a distraction to the people that are around you that really do still need a lot of work on trying to figure out how to get those spectra solved. So this is a new thing. Aha, there we go. Okay, just so you know, there's 2 buttons up here. One says blank and the other says blank. So you're never sure which one you have to push. Which blank? All right, so to start with, we'll start with mass spec. There are a couple things I do want to say about mass spec. So remember that this is the first one that is not a spectroscopy. Just that's a little tidbit for you. It's spectrometry, not spectroscopy. So if you want to sound really smart, you'll say mass spectrometry. That's pretty cool. That shows you know a lot already. So mass spec, there are a few things that we can get from it. So go. Tell me what you get from mass spec. Here's a representative mass spec. But what can you get? You get the molecular ion peak. Great. So the molecular ion peak, which is generally tagged as a radical cation, and often the little m placed right at the furthest peak to the right. Not always the furthest peak to the right, but generally the first major peak to the right. Furthest to the right in the spectrum is what we call the molecular ion peak. The molecular ion peak is probably the most important to us because it gives us the mass of the intact molecule. So that's a way for us to, we can use that information to kind of figure out the formula if we need to. So number 1, that's good. It gives us the mass of the molecule. All right, what else can I tell from it? This might give you a hint because there's a specific mass spec here shown. There's a halogen. Okay, great. So really, you can actually determine functional groups, some functional groups, very quickly with mass spec faster than you can with IR or NMR. Okay, and that's actually why it's really helpful. So sometimes on problem sets down the line, we might give you some information on mass spec. Look at that. There's a reason that information is being given to you, right? Because you can use that to get something out of that. So the functional groups that you can determine are 1, the halogenated compounds. So you can determine sort of an alkyl chloride, which is what we have here, and I'll show you that in just a second, and an alkyl bromide. So these are the 2 of which this slide is a representative example. will go online right after class today. I didn't set it ahead of time. I wasn't sure if I was going to do one, and then I thought, oh, it's going to be a really good idea to have some pictures, so I decided last minute. So I'll make sure this goes online right after class. So you don't need to copy it all down and all the rest of that, right? Just take notes. So first and foremost, do anyone wonder if I could like get out of here? Isn't that fun? The fun that we have in here. Okay, so the first thing to note here is the furthest right. Does everyone see those feet 78 and 80? Okay, 78 and 80 should really be, and they will be, if we're an exam, I tag an M next to the 78, okay? 78 and 80 are the two actual molecular ion peaks. 78 is the major one, okay? And the 80 would be what we call an M+2 peak. So the M to M+2 ratios tell us what type of alkyl halide this is, okay? Right now we see, and that answer obviously wouldn't be given on your exam, right? But right now you can see that the 78 peak is about 3 times as large as the 80 peak. Does everyone remember why that is? Good question. Yeah. Okay, from the isotopes of chlorine. That's exactly right. So there are 2 isotopes that are naturally occurring for chlorine. One is Cl35 and the other is Cl37. The Cl35 has 75% relative abundance, and the Cl37 has 25% relative abundance. Hence the 75 to 25 ratio, right, of these peaks in the mass spec. So these M to M+2 ratios are going to specify what type of halogen you're looking at. The only 2 you're going to be held responsible for are the chlorinated compounds and then the brominated compounds. Now, I don't have an example of the brominated compound, but does anyone know what 2 isotopes of Br there are? No one knew this was going to be a quiz show today, right? There's a quiz show every day, so get prepared. Anyone? Anyone? Yeah. So close. I really like that answer. 79 and 81. Good job. Good job. It wouldn't get you the $1 million on Who Wants to Be a Millionaire, but it does get a lot of fanfare, I promise you. So 79 and 81 are the 2 naturally occurring isotopes, and they come in a 50-50 ratio. So what you'll see for a brominated compound in this M to M+2 area is a 1-to-1, right? Each of those peaks, M and M+2, will be equal in height. So you can identify very quickly if this is a chlorinated compound, or if it contains chlorine, or if it contains bromine. Very useful to us. So 1 is functional group determination of these halogenated compounds. Does anyone know what other functional group we can determine very quickly? Yep, we're going to teach you how to answer questions in class by waiting. You answered a question. We're going to try and get someone else to raise their hand. Please don't make me get flashcards. Yeah.
If there's a nitrogen in it?
If there's a nitrogen in it. So you guys know so much more than you think. Okay, great. If there's a nitrogen in it. It has to be an odd number of nitrogens in order to have an odd molecular ion peak. Does everyone see the molecular ion peak, which is tracked there at the furthest right, has an odd mass. Anything that contains an odd number of nitrogens is going to have an odd mass. So that's going to mean to us any amines and amides. Everyone remember the difference between amines and amides? Amines are just a carbon backbone with an N off of it, right? And an H2 would have R groups off of it. And an amide is a C double bond O and H2. Okay, so anything that has an odd number of nitrogen, of which those 2 functional classes do, amines and amides, will have an odd mass peak. So if you're told that your molecular mass is something odd, you automatically know that you have an amine or an amide. So now you've got to be guessing which one it is. Okay, we're going to use other tools to do that. So this is quick and dirty ways that you can identify these functional groups. So this is the summary here of mass spec. Number 1, mass, great to have, very useful in terms of figuring out the formula, and functional group determination of a few functional groups very quickly. Okay? Are there any questions about this? Does anyone know what fragmentation pattern is going to lead to the base? Just kidding. Okay, we won't do that. No fragmentation. We can talk about it if you want to, but no fragmentation. Okay, so let's move on to IR then, right? So the next spec that you probably ran into was IR. That is a spectroscopy. So IR spectroscopy, you've done a lot of at this point. point, so you know a lot about it, but I'm here to remind you of a few things, okay? One is you're really probing the different types of movements there are in a structure, okay? Minimally, the simplistic way to look at a structure and to get into actual bonds is to think of these bonds as a spring, two atoms on a spring. Okay? And if you've had physics yet, what's the probability of us having physics here in this class? How many people have had physics? Yeah, okay, that's good. All right, that's a good start. That's a good start. In simplistic terms, we can actually use something called Hooke's law, a modified version of Hooke's law, to actually talk about the vibrations of bonds. Bonds are not static. Please remember, they are not entities that are held together, right, and locked. They actually are moving, right? They stretch, they contract, they stretch, they contract, and three-point systems bend and wag and twist and do all sorts of funky motions, as you probably saw some crazy motions there on the previous slide. But importantly, we know that we can get information on the types of vibrations that occur in these molecules, and these vibrations that we can actually see with IR spectroscopy are related to two important things, okay? And that is both the force constant of the bond, so here is K, that's the force constant of the bond. So if you really want in your notes right now, you want to put this symbol, which is frequency with a bar over it, right, which is reciprocal wavelength, it's wave number. That's the access in an IR spectrum, right? So its number, its value is, skipping this, that doesn't matter, is related to or proportional to the force constant of the bond, which means how strong the bond is. And you know something about bond strength. What type of bond is strongest? Triple, double, or single? Triple. There you go. Okay, so obviously a triple bond is stronger than a double bond, which is stronger than a single bond. So if you ever look at your IR spectrum, where do single bonds fall? They fall in a different place than double bonds and then triple bonds. That's because you have a proportionality here. And the other piece is reduced mass. And that's in the denominator. And reduced mass formula, its placement in this formula, basically tells us that lighter atoms will happen to have vibrations that are further to the left in our axis, so more toward 4,000 wave numbers. That's in essence what it means. If you play with the formula, you'll actually see that. But we actually then have information, right, about the IR axis. Where do we find specific things in the IR axis? So you were asked last term to know a few of them. Now in the lab, you were expected to know a whole bunch more than you were likely asked, I'm guessing, in the lecture environment. So there, we'll outline here what I'm going to expect you to know in the lecture environment. Okay? Number one, we are never going to pay attention to anything below 1400. That's what we call the fingerprint region. I know you went down there. I know you look at stuff down there in the lab. That's really hard to dig out stuff, okay? Not easy to do. So we're going to ignore it. Just put a big X by it. You're not going to do anything down there. There are interesting things you can find. You can find the halogens. You can find a lot of ether stuff, you know, when you're looking for stuff on ethers, but we are ignoring it. There are three main regions we're going to look at, okay? Region 1 is going to be the region in and around 3,000. In and around 3,000 will give us information on the type of CH stretches or carbon CH bonds that we have in the molecule. In essence, we can see if this is sp, sp2, or sp3 hybridized by stretches we see in and around 3,000. So on this slide, we're looking in and around right here. You see in green it says CH stretch, right? So we're looking in and around here. There's a couple things to note, okay? One is that most molecules, all molecules really, I mean, almost all molecules, have a CH stretch that indicates there's sp3 carbons in there. Almost everything has sp3 carbons, right? The question becomes, are there any differently hybridized carbons? Are there any sp2 carbons? Are there any sp carbons? Because that begins to grow out what potential functional groups I have, okay? So let's just skip ahead here and I'll show you a couple of examples because I think it's best to learn by example. This is an example of an alkene. Okay, so you can see this is cyclohexene, and you can see that the CH stretching that is no longer just below 3,000. Let me toggle back here for a minute. No longer just below 3,000. Keep your eye on that 3,000 here. You can see that in this slide here, all the stretching in that area is just below 3,000, meaning to the right of 3,000. And when I come up to the alkene, I can see that there's some stretching below 3,000, but now I see this peak that's at about 3,100. And this ranges, but you can see how it's a sharp peak just above 3,000. And that's an indication of an sp2 carbon, therefore it could be an alkene. It could also be an aldehyde. You gotta remember all your functional groups. If you're a little functional group queasy or, not remembering your functional groups, please, that's something definitively you need to review. But this is an aldehyde, and you can see it has an sp2H stretch, sp2 carbon H stretch as well. So seeing that is an indication of certain types of functional groups. But more importantly, this semester we're going to be looking at a lot of benzene rings, right? Aromatics abound, and you can see how this stretching gets kind of crazy when you look above 3,000. Now there's not only a single stretch, but there's a whole bunch of stretches, right? It's like a mass of peaks just above 3,000. This pattern is a good indication that you have an aromatic present, a benzene ring, and that's good evidence, because what you're doing when you're asked to come up with a structure is to start amassing evidence. So this is some evidence that might lead you to benzene as a potential structure. Okay? So this is one region you're going to be asked to look at to sort of make a decision on the different types of hybridized carbons that exist in the molecule. The second is you want to look way above 3,000 for not these sharp stretches that we see for these CH stretches, but rather stretches that are indicative of alcohols and NH groups in our molecule. So you can see that to the left there in about that 3,500 region, there's that green box that says OH and NH stretch, right? That's where you find your OHs and your NHs. So if we look at some examples down here, this is an example of an alcohol. You can see the alcohol peak is much different than those CH peaks, right? The CH peaks are sharp, okay? They're definitely sharp. See how the bottom looks a lot different than the wideness of the OH peak, okay? So those OH peaks are generally broad, and they take over that region in the spectrum. They'll generally fall from 32 to 3,700, somewhere in there, okay? But they always look like this, broad, intense, which means they come almost all the way to the baseline, right? And that's a sign of an OH. Now, NHs are a little bit harder, which is why I brought up the mass spec. If you have an odd molecular ion peak and then some stuff above 3,000, don't guess an alcohol. That's just not smart, right? You know there's a nitrogen in there. So you got to start guessing, right? There's a nitrogen in there and looking for these NH peaks, okay? So this here is a primary amine, okay? If you were not told last term, I'll remind you really quick that amines can either be primary, secondary, or tertiary. Okay? You see the difference between primary, secondary, and tertiary as losing an NH bond as we progress from primary, secondary, to tertiary. So a primary amine has 2 NH bonds. A secondary amine only has 1 NH bond, and a tertiary amine has 0 NH bonds, okay? So you're not only going to need to be able to scan for these NH bonds, but you're going to need to have to scan for whether or not there's 2, and I would track that as a primary, 1, I would track that as a secondary, or 0, and then there'd be nothing there, and you might not even guess it's an amine, right, but for the mass spec. So you got to be smart. Right? Those two pieces kind of go together, mass spec and IR. You've got to really be thinking between them, toggling between them. Okay? Does everyone see that? Any questions about the difference between an OH and an NH and the importance of looking in that area? Yeah.
Yes, I'm kind of not really sure how to determine whether the amine is a secondary or tertiary or primary.
Okay, so this amine here has an ethyl group attached and a methyl group attached,
Okay.
and then a hydrogen. This guy has 2 ethyls and a methyl, right? So there's no hydrogen here. So you're literally just counting the number of hydrogens. Okay? Yeah?
So how would you say the iron but not the primary?
Great. So this is primary because I see 2 NH peaks. Okay? If I had 1, it would begin to look like an alcohol, but it wouldn't exactly. It's not. NHs are tertiary, it would be what we call IR absent. It's not, you wouldn't see it in the IR, so you really would have to have other evidence to know it's there. Okay? Yes?
Could you just go over again how the difference between OH and NH?
Yes. So an OH is always going to have it's almost like qualitative, and that's what makes it so hard. But an OH generally has this broadness to the peak. Okay? You see how in NH, if there's a single NH, let's say it's a secondary amine, this won't be as broad. So if I look at an OH, right, which on this slide looks like this, if I had a secondary amine, it would probably look something like this. See how it won't come down as far toward the x-axis. It won't be as broad, right? It's going to look qualitatively different. So it's really, and you sort of have to get a feel for it. You have to be like, oh, and you get better at it. But so the OHs are going to be more intense and broader, and the NHs are going to be less intense and narrower, less broad. Okay? All right, so the last region that we're going to look at is the carbonyl region. Okay, and you're probably all accustomed to looking for those carbonyls, but if you haven't recognized, a lot of the chemistry we do this term is of carbonyl-containing compounds, ketones, aldehydes, halides, esters, etc. So get used to looking at the carbonyl region here. So 16 to 1800 is the last one. We'd ask you to definitely be able to identify any carbonyl peak. Okay, a carbonyl peak looks a lot like an NH peak, except it's more intense, right? It doesn't have the broadness of the OH. It doesn't have the sharpness of the CH peaks, right? It's sort of in between them, and you'll always find it between 16 and 1800, okay? Should come almost to the baseline. Sometimes you see peaks in there that are really weak, and you want to assign them as carbonyls. Be very careful of that. Find corroborative evidence before you make that assumption. If it's not clear, absolutely clear, don't assign it as such. Okay? Most carbonyl-containing compounds give very clear IRs. Where we run into a little bit of trouble, and I don't teach the lab, which you probably know, but is in the lab. So be very careful before you look at some weak peak in that region and say it's a carbonyl, unless you're sure, right, from corroboration that the carbonyl is present. Now, I have a little exercise that we can try here for a minute. My question to you, and this was on the 231 review packet, my question to you is this, and we've said enough today that you probably might be able to get this answer here. If I were to look at two carbonyls, here's one, let's say we do, I think this might even be the question that's on the review, but it's the most disparate, the most obviously different. If I were to look at these two carbonyls, the question is, which one is going to fall more towards 1600 in this region, this carbonyl region? So which carbonyl is going to have a peak more towards 1600, and which of these is going to have a peak more towards 1800? So where are they going to fall in this region? Okay, they're both carbonyls. So we have to have a way of sort of discerning within that region which is going to fall more towards 1600 and which is going to fall more towards 1800. Yeah. Okay, what would make you think that?
Just because when we were talking before about nitrogen, it was
Oh, qualitative from there. Actually, it's the opposite, but I see, because you took a qualitative approach, and I appreciate that, yeah.
maybe we go back to one. One you said that if it's lighter, which is the plate one that has lighter components, so we'll look into that. So I'd say that the nitrogen would be the
Ah, okay, so we would go on that. That's actually really smart. That actually wasn't, it's a very good answer. This is a very good answer, and that defies that. So we're going to have to think about that for a minute here. Yeah.
I would say that the ketone would be would fall under 16, and the amide would fall under the 18 because of the NH.
Okay, so you're all, in essence, you've all gone to the same answer, and that answer is actually not right. So let's go and say why the answer is right or the opposite. Generally, this is going to fall more towards 1800. These generally are about 1750 or something like that, and this is going to fall more towards the 1600 range. They're actually about 1610, 1650. Okay? Here's the reason why. You were the closest, so So it was like, ding, 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 ding. I feel like sometimes we play Price is Right, and I can almost be like, you're the closest, go! But the answer does come to modifies Hooke's law, but it comes through resonance. Your lovely answer to so many things in chemistry, right? Resonance. So if I look at these two structures, only one of them has a resonance structure, the other does not. The resonance structure actually is of the amide, where I can actually resonate this electron pair that's on the nitrogen and draw a contributing structure that certainly isn't going to contribute as much as the original structure. I totally agree that if I were to draw a resonance hybrid or to think about what this molecule looks like, I certainly would note that it's going to have more of this character than it is of this character, because this contributing structure, everything neutral, is more stable, right, than this one here on the right. But if this contributes at all, you can see that this carbonyl bond is no longer a double bond, is it? It's a single bond, which in essence means that this has more double bond character in that carbonyl, and because it has more double bond character, it's a stronger bond, and you expect it to come more toward the right end of this region, more toward 1800, because your proportional, the value that you see for its stretch is proportional to its bond strength, okay? Now, in answer to the lighter, heavier thing, when you look at the reduced mass, you don't see a huge disparity there. They don't separate themselves all that much, whereas changes in bond strength really make leaps and bound changes in where you're going to fall on the IR axis. But it's a great answer. Love that answer. Okay? There are questions? Yeah?
When you said that it has more double bond character in comparison to what?
In comparison to the amide. So this amide, I would say 90% of the time, right, if I had to take 100 pictures of this molecule, maybe, I'm going to go even higher, 95 of them are going to look like this, but 5 of them are going to look like this, which means some of the time this bond here is not a double bond, it's a single bond. So that reduces its double bond character. So that, in essence, that makes this molecule have more double bond character, a stronger bond, and therefore further to the left in our IR axis. Okay? More toward 1800. Questions about that? You can chew on that for a while. That's also in the 231 answer or review.
So if there's a stronger bond, the wavelength is longer, bigger?
Yeah, that's exactly right. So it says when bonds are stronger, it's going to take a higher wave number, right, of light. You don't usually classify light in wave numbers, right? It's either wavelength or frequency. This is reciprocal frequency, which means it's proportional to wavelength. So yes, it takes a higher wavelength of light to match the vibration that's being seen there for stronger bonds. Okay? All right. The only other functional group that maybe you didn't see last term is this one, and this is a nitrile. Does everyone see that molecule there? It's C triple bond N, C triple bond N. That nitrile there is a functionality that is related to the carboxylic acid family. And that nitrile has a very specific peak. The C triple bond N stretch actually falls in an area that's pretty much absent of anything except for the nitrile. You don't see anything else in this region, ever, except the nitrile. And it really almost always rides at that 2200, 2200, 2200, 2200. So if you take a scan of the IR and you see that peak at 2200, assign it as a nitrile, okay? And we'll be looking at this too through the term, because this is one of the functionalities that we do talk about this term, okay? So you might not have seen that this last term, but it's a nice, easy one to identify with IR spectroscopy. Would you expect it to have an odd mass number? Yes. So that reminds me that maybe we should add nitriles. So if you're keeping notes, Alice, of what's on the board, please go back. This does have one single nitrogen, so you'd expect it to have an odd mass number. Okay? So it has an odd mass number and a nice sharp peak of 2200, nitrile hands down. Okay? Hands down. So please edit your notes, make sure you've got that in there. Did you get your question? Go ahead. Yes, the stronger the bond, the higher the wave number, which means the further to the left you see if there's an interplay there in Hooke's law, right, between the strength of the bond and the atoms that are attached. The hydrogen, because it's so light, does push it way up there. Yeah. You gotta really like look at all of that formula. It's crazy. It's crazy how they move. Okay, so this is pretty much what I wanted to say about IR. Are there any questions? Yeah.
Does it work the other way? If you see an odd peak, it's always going to be cyanide and lunar nitrogen?
An odd peak. What do you mean odd peak?
If you see an odd mass peak on the right side,
Yes. Yes.
it will always be that.
Yes.
It works like that.
Absolutely. One of these. Go look for more evidence, but it is one of these for sure. Yes. There are some more hands up. Keep going. Yeah. There are times where you have nitrogens in the compound and you have an even mass peak. The reason that would be is because you have two nitrogens, right? So we're not after tricking you, though. I mean, if you take more advanced coursework, yes, you will see compounds that have more than one nitrogen in it, right? 2, 3, 4, 5. But we will be a nitrile, an amide, or an amine. I promise you. Okay? There's one more hand up. Yeah.
We talked about the CHS with sp3 and sp2. What about if you're looking for sp?
Yeah, you know, alkynes, no, we're not really. I mean, yeah, they exist. I don't want to suggest that. You know they exist even further to the left, right? They're nice sharp peaks, but I can't imagine giving you an IR of an alkyne. Okay? All right, barring any more questions, we get to move on to NMR spectroscopy, which is my absolute favorite in the entire world. This is what I did my graduate work in, my postdoctoral work. It's the bomb, okay? So, there are 4 important features in an NMR spectrum, okay? It's probably stuff you remember from last term, so we'll review really quickly. So, the first is number of unique environments. I do have something to say about that here in just a second, but you know that for every unique set of hydrogens, there's a unique peak in the NMR spectrum. So, in some cases, especially on multiple choice questions, of which your pre-assessment is, you can sometimes just count unique environments of all the answer choices, right, and backtrack to the right answer. So I'm just telling you that if you were in a multiple choice setting, that is one way to go. I've seen that on the MCAT as well, right? They just simply give you some choices of what the spectra, here's a spectrum, here are some choices of the molecule. If you just count number of unique environments in each one of those answer choices, and the number that you see in the NMR spectrum, you're usually good to go, all right? Second piece is integration. I'm not going to talk a tremendous about that this term. The integrations will be given to you on your exams, problem sets, everything. Where you are asked to integrate is the lab, okay? So I will teach you quickly how to integrate on Friday, and there's a handout on the back of your packet that goes through all the steps, so that you'll be able to integrate for any lab exercise you'll be asked to do. But suffice it to say, every unique peak set will say 3H, 2H, 1H, right next to that peak set, all right? The third is chemical shift. You know that chemical shift is a unique identifier. It gives me some information about those protons and their relative location in the molecule. That's part of what we use to put a structure back together. And one of the bigger parts probably is multiplicity, right? And multiplicity is the influence of neighboring protons on the proton set of interest, okay? Again, this is coming out. You don't need to copy all this down. You can get just the highlights there. Unique environment, integration, chemical shift, multiplicity. This is all borne out in a typical NMR spectrum, okay? So while we ride around this presentation, we're going to be using this molecule here, which is ethyl acetate, okay? This molecule, this first slide is just to say this molecule, uniquely identified by color here, has 3 unique environments. One is the CH3 group that's highlighted in green here. One is the CH2 that's highlighted in red, and one is the CH3 highlighted in blue, okay? The blue and the green are different, right? Because the green is a CH3 group next to the carbonyl, directly next to the carbonyl, right? And the blue CH3 group is next to a CH2, which is then next to an oxygen. And that's different, right, than being next to a carbonyl, okay? So they are unique environments, and they should come up as 3 unique sets, okay? And they are actually assigned here color-coded so you can figure out which unique set is which. But simply, all I want you to remember is the unique set concept, okay? Which hopefully that one's okay. Now, one piece where we get into a lot of trouble, do these terms look familiar? How many people can tell me these terms look familiar? Okay, that's not bad. Okay. The concept of enantiotopic and distereotopic is important to NMR spectroscopy. Okay? Enantiotopic protons are important in biochemistry. Or the biggest example is lactate dehydrogenase, right? Or alcohol dehydrogenase, which picks up a specific proton, always the same one in the molecule three-dimensionally, as it makes, the ketone at that position. So that's one specific example of how enantiotopic groups differ from one another. But that's unique to biochemistry because that's a chiral environment, right? But in an achiral world, outside of the human body or outside of nature, just here in our classroom, distereotopic groups are actually identifiably different by NMR. Two groups that are what we would consider distereotopic have different chemical shifts. They're a little bit different from one another, and that's actually useful information if the NMR spectrum becomes a little bit harder, right? You need to remember that distereotopic groups are different from one another. Now, this takes a while to review, so if you're a little fuzzy on this, which is why the slide is here, come on in. We got to talk about it. We have to talk about what the difference is, how you would identify distereotopic groups, how you would identify enantiotopic groups, and how that plays out. I'm happy to do that. It's going to be on a problem set, don't worry, but review it and think about it and go review it in your book. Yeah?
So there's only different chemical shifts in the distereotopic group?
That's exactly right. Isn't that crazy? Enantiotopic groups do not have differences in chemical shift. They are considered identical for NMR. So that would be a CH2 group, right, on this molecule. That would be a CH2 group where both those hydrogens share a chemical shift. Whereas down here, HS and HR in the distereotopic group, those two protons would have different chemical shifts, slightly different from one another. You can ask your follow-up question after class. I'll make sure we get to you, okay? So the next concept, past unique groups, is to remember about chemical shift. Chemical shift is all about how much electron density you have around your nuclei of interest, okay? Remember the concept of shielding and deshielding, okay? And that's related to how much electron density there is around a given proton set, okay? You're sticking your entire molecule in an external field, right? The B0. You stick it in a magnet, just like if you get an MRI and go right into the bore of the magnet, right? Molecule does the same thing. It goes right into the magnet. And it feels an external shift. And according to physics principles, right, if you stick electrons in a magnet, they begin to move, right? Electrons move. And according to the right-hand rule, they actually create this tiny magnetic field against the external field. That's all related to the vector dissection of what's going on physically in the molecule. But regardless, what I can tell you is the more electron density there is around here, the larger the field is going to be against. The less electron density, the smaller the field is going to be against. So you remember you used this terminology when you looked at your NMR axis. That was shielding and deshielding, right? Hopefully you used that. So your axis went from about 0 to 12 parts per million, right? And we said that if you were toward 0, you were shielded, which meant that you have lots of electron density around you, meant that you were likely in an area with just a lot of CH2s next to you, or CH3s, not anything electronegative at all. And as you moved to the left, you became what we say deshielded. So this terminology comes from this exact concept of what that nucleus, that hydrogen nucleus, feels, okay? And it plays out in a very specific way. So if we look at these three chemical shifts for this molecule, you see they fall in different areas of this 0 to 12 part per million axis, okay? The least deshielded, the most shielded is the blue, okay? And the reason that set is most shielded is because it's next to a CH2. It isn't next to an electron withdrawing group. There are two electron withdrawing groups in this molecule. One is the carbonyl, it's what we would call a weak electron electron withdrawing group. Does anyone know another weak electron withdrawing group? Carbonyl is one. What? Halogen would be considered strong because it's very electronegative. What? An amine is a weak electron withdrawing group. Yep. They have benzene. A benzene is another weak electron withdrawing group. I would also say a cyano group. Okay, so those are examples of weak electron withdrawing groups. They're going to pull some electron density toward them, but not tremendous amounts. Okay? How about a strong electron withdrawing group? Someone threw one out. I already assigned that to halogen. What else? Anyone know another atom that might be considered a strong electron withdrawing group? Yeah. Yeah. Hydroxide, an oxygen. Great. An oxygen is a strong electron withdrawing group. Great. So in this molecule, I have a carbonyl, a weak electron withdrawing group, and an oxygen, a strong electron withdrawing group. Okay? So my blue CH3 is next to just a CH2. It's not next to either one of those electron withdrawing groups, so you're expected to find it most upfield, right, toward one. So when we say shielded, we also use terminology upfield, right? So it's the most upfield, which means towards 0 parts per million. It's towards 0 parts per million because it doesn't have anything drawing electron density toward itself. Okay? And as you come down, you can see the influence of stronger and stronger electron withdrawing groups. Okay? This green CH3 here is up at 2 parts per million. It's next to the weak electron withdrawing group, so it brings it further downfield. And this red CH2 is next to the oxygen, the strongest electron withdrawing group I have, all the way down at 4. Okay? So I would chunk your NMR access, and you will not be given chemical shift tables in your exam because you don't need them, right? You got to be able to learn on your own. You get so married to those numbers that when they're not those exact numbers, you just give up. Okay, so no chemical shift tables. We're going to chunk our axes here. So we have a 0 to 4 chunk. I have a 4 to 6 chunk. I have a 6 to 8 chunk. And then I have a couple things that I'll look for up here, around 9 to 10, and probably 10 to 12. Okay? If I have a peak at 9 to 10, definitely an aldehyde. It's specifically the hydrogen that's off of the carbonyl. Okay? So it's this guy right here. 9 to 10, definitively an aldehyde. That's it. Okay? It also will not have a track next to it that says exchangeable. Okay? Sometimes we use that sort of language to give you information that it's an OH, exchangeable. It exchanges with D2O. There'll never be anything tracked at a peak at 9 to 10. That proton will never exchange. Now, a carboxylic acid, though, will. So this peak down at 10 to 12 is carboxylic acid. It not only exchanges, it's also broad. And like I said, it'll have an arrow that points to it and it says exchanges with D2O. That's a sign to you that it's an OH. Its placement tells you it's specifically a carboxylic acid OH, and that's what you want to track it as. Okay? So this is actually important information. Now, of my other chunks, okay, I know that these down here are hydrogens that are attached to sp3 carbons. All hydrogens attached to sp3 carbons will always fall between 0 and 4. All right? Hopefully you already know that any peak at 0 is actually TMS, which is tetramethylsilane. It's the reference that we use. Exit out, it means nothing. It won't have an integration next to it. It won't have anything. Put a little X on it so you don't forget to ignore it. All right? But where I am in this range depends on what I'm next to. Okay? 0 to 2 parts per million really means that I'm not next to anything. Not a weak electron withdrawing group, and certainly not a strong electron withdrawing group. I'm just in an alkyl environment. 2 to 3 generally means that I'm next to, this region here means I'm next to a weak electron withdrawing group. So I'm next to a carbonyl, or an amine, or a benzene, those sorts of things. And 3 to 4 basically says that I'm next to a strong electron withdrawing group. I'm next to an oxygen, I'm next to a halogen. Now, there is one caveat there. 2 weak electron withdrawing groups add up to 1 strong electron withdrawing group. For instance, if I look at, say, something like this, something like this, these two hydrogens here, they're what I would track as a benzene next to it on the left side and a carbonyl next to it on the right. They're next to two weak electron withdrawing groups. They're going to come up to that 3 to 4 region. Okay? So two weak electron withdrawing groups add up to a strong electron withdrawing group. You got to be careful in some cases because that causes you some trouble. But noting that, you should be fine. Okay? Now, within each given region, so let's just talk about a given region here. In this 0 to 2, you should note that CH3 groups fall more upfield in the region, followed by CH2s, followed by CHs. This is the general trend in every grouping. Okay? CH3s will form more upfield in that little region, then CH2s, then CHs. It has to do with relaxation behavior. Don't talk about, don't worry about it, but it is a good guide to use. Okay? So this may or may not be helpful. You may never need to worry about this. I'm just putting out things that you might find helpful. 4 to 6 is where you find these sp2, hydrogens off sp2 centers, your alkenes, right? So be looking for those there. Specifically, this 6 to 8 is the benzene region. So these are all hydrogens that are off of the benzene itself. Okay? So you need to know how your axes are chunked and be able to use this information. Again, an NMR chemical shift table will never be attached to any exam. So you've got to just sort of get comfortable with noting where things are and having some meaning behind it. And we'll be doing the exercise on Friday without a chemical shift table. So we'll give you practice there. Okay? All right. The last thing I want to remind you about is multiplicity, right? Multiplicity is actually very useful in assigning. If I couldn't use, I'll get you out here. If I couldn't use chemical shift, number of unique environments, or chemical shifts to make any distinguishment, I would then go to multiplicity. Multiplicity would be the last thing that would allow me to separate in a multiple choice environment one answer from another. Okay? I remind you that simple multiplicity is following just the n+1 rule. Okay? And the reason for that, if you have been told or not told, is because each of the neighboring protons, whether or not they're with the field or against the field, influences the nuclei of interest, which is where the +1 comes from, n+1. Okay? So multiplicity simplistically follows what we would say as Pascal's triangle, right? That if I had HA here and it wasn't next to any protons, it would be a singlet. If HA is next to HB, I'd have HB1 being with the field, and another option to be against the field, so n+1, 1 HB, a doublet. By 2 HBs, I'd be a triplet, but does everyone see the pattern is 1 to 2 to 1? This is the actual reason, okay? The 1 to 2 to 1 comes from the fact that I can have both neighboring protons with, both against, those are the ones, and then I can have one with and one against, or I can swap those one with and one against, which is why there's two possibilities in the center, right? And you get the 1 to 2 to 1. So that's the reasoning behind that. But simplistically, you should be able to count up the neighboring protons, add one, and gain the multiplicity of the nuclei of interest. Now, if you look here at ethyl acetate, you'll see that this actually follows. The green CH3 is a singlet because its neighboring carbon has 0 hydrogens, right? So it's a singlet. When I look at the red here, okay, that's the CH2. It's next to a CH3 on the right side with 3 protons, right? Nothing on the left, so I don't have to add anything else. So 3 total protons on its neighboring carbons. 3 plus 1 is 4, and Pascal's triangle is this pattern, right, symmetrically for the quartet, okay? And blue CH3 is next to 2 protons, and hence we become a triplet. So we're 1 to 2 to 1, okay? Now, it's a little bit harder for sure, but we are going to be talking about this next class. This is a little spacer slide to remind me that there's advanced coupling. How many of you dealt with advanced coupling last term? A doublet of doublets, a doublet of triplets. How many of you have seen that before? Okay, we're in trouble then, right? Okay, so why don't you see if you can't figure out or help yourself figure out this last portion of the presentation, See if you can't read ahead on it. I will start here on Friday before we go into the packages.